Henon map. I consider a state space system in the discrete time given by this recurrence equation. A set I is said to be invariant if its image by the evolution function is itself. I have to prove that if I1, I2 are both invariant, then their union is also invariant. So for the first question, I assume that I1 satisfy f of I1 equal I1. And I assume also that it is the case for I2. If I consider the union f of I1, I2, so due to set theoretical properties, it is equal to f of I1 union f of I2. Now, this is equal to I1 and this is equal to I2. So it means that it is equal to I1 union I2. As a consequence, the image of the union is equal to the union. I1 union I2 is an invariant set. Question number 2. Given a set A, I have to show that there exists a largest invariant set which is included in A. And this is denoted by inv of A. So second question. I have a set like this, which is A. The image of A may be something which is not A. For instance, it may be like this. It is f of A. In this case, A is not invariant. But maybe here I have some sets, such as this one, such that the image by f corresponds to itself. I may have also another set, like this one, such that the image by f is also itself. I know that the union of these two sets is also an invariant set. As a consequence, there exists a unique largest invariant subset of A, which corresponds to the union of all subsets of A that are invariant. And this set is unique and can be defined because the union of invariant sets is an invariant set. Question number 3. I consider a sequence given by this recurrence and initialized at x of 0 equal to A. Now I have to show that this sequence will converge to the invariant set. I have the sequence f of k plus 1 equal f of xk intersected by A and initialized as x0 equal to A. So let me draw this. I have the set A and I compute its image. So this is f of A. I intersected the two of them, so I will obtain this set. So this one corresponds to x of 0 and this one corresponds to x of 1. Now I take this set x of 1 and I compute its image. So its image may be something, let's say, like this. I intersect with A. so the blue one, I will obtain this. This corresponds to x of 2, and so on. So this sequence will converge, and I have to show that it will converge to the largest positive, the largest invariant set of A. So for this, I observe that this sequence is decreasing with respect to this relation, this order relation. So the sequence is of k is decreasing. As a consequence, since there exists a smallest element in the set of subset of Rn, then it will converge. So I think it's quite intuitive, but it corresponds to a well-known Tarski fixed point theorem. So we'll assume that it is true. As a consequence, we have x of infinity which exists, and now I have to show that this corresponds to the largest invariant set of A. For the first part of the proof, I will first show that the largest invariant set of A is included in the limit. I will do it by induction. So first, by induction, I have to, for k equals 0, I observe that, of course, invariant of A is included in x of 0. And x of 0 is included in A. Okay. So this is the first step. Now, what I want to show is that I assume that invariant of A is included in x of k. And I will show that it is true for k plus 1. So if I have this, it implies that the image by the image f of invariant of A is included in f of xk. So if I intersect by A, here and here, I still have the inclusion. So since the image by f by the of invariant of A is equal to itself, so this corresponds to invariant of A. Since the invariant of A is included in A, all this also corresponds to invariant of A. Now this corresponds to xk plus 1. So I have shown that invariant of A is included in xk plus 1. Since xk plus 1 is also included in A, okay, so it will go up to infinity. And by induction, I show that invariant of A is included in x, the limit of the sequence. So it was the first part of the proof. Now the second part of the proof, I have to show that x, the limit of the sequence, is included in invariant of A. So we have, to prove this, we have, due to the fact that I have the limit and the limit converge, I have the image by the sequence of the limit is equal to the limit. Moreover, I know that this one is included in A. As a consequence, x of infinity is a subset of A which is invariant. Now, I know that since it is invariant and is in A, I know that it will be included in invariant of A because invariant of A is the largest invariant set. So it is a union of all invariant sets. As a consequence, I have proved this. And from the first part of the proof, I conclude that x infinity is equal to invariant of A. Last part of the exercise, I consider a specific function which corresponds to the Henon map, so the f. I know the two parameters, and I have to take the previous sequence and to try to draw an approximation of the largest invariant set of the discrete time system. And the set A to be considered is a box -2, 2. So I take a box like this, corresponds to A, and I have to compute the largest invariant set of A. So it satisfies this equal to this. So the algorithm I propose is to take many points here and to represent A by a cloud of these points. Now I will compute for all these points. I need to compute f of A. So f of A, a simple possibility is to compute for each of these points the image. I will generate a new cloud of points. And I will only keep the points that are inside A. So I will have an approximation of f of A. So this one will be called, from the sequence, x0 correspond to A. And I will generate this one intersected. So here it's x0 intersected with A. And it will correspond to x1. So it means that in this cloud of points, I will remove all points that go out of A, and I will keep all those who stay inside. So it may correspond, for instance, let's say, to this set. So this corresponds to f of x0 intersected with A, and it corresponds to x1. And I will continue like this. I will take this set, I will compute its image, I will intersect, so remove all the parts that are outside A, and I will form a new set which corresponds to x of 2. And x of 2 is equal to x of 1, f of x1 intersected with A, and so on. So it corresponds exactly to the previous sequence I have introduced just before. This is why I propose the following Python program. I have my evolution function, which is given by x3 plus 1 equal f of k, and this function corresponds to f. The parameter of my Henon function are given by a and b given here. I initialize the figure as this because I know that it contains the attractor. So I will just show what I have inside this box. So now I consider a cloud of points, but I will not memorize it. I will take points one by one. I take randomly a point inside the box -2, 2, -2, 2. So randomly I take a point. So it is one element of this cloud of points. And now, instead of computing with this cloud of points, I compute for each point. I will compute not up to infinity, but 100. So if this point goes out, I will stop its evolution. It will be outside and I will not draw it. Otherwise, I continue. So for some points, I continue. And since this box is, so the visualization box is inside this one, I will only see those that have converged to that stay such that all the sequences, such that the limit of the sequence stay inside this one. So they did not went out this box. So I will draw them magenta, and I will see with this, I will see the attractor. This is my Python program. I run it. And this is a representation of the attractor. If I take many points, I will have a representation of the attractor here. Invariant of A. Here A was like this. It was a box. A equal -2, 2, -2, 2. And the image by A of this invariant set is itself. Now there exists probably many other invariant set in A. For instance, this one may be invariant. This one may also be invariant. The union of them will be invariant. But this set cannot be invariant because all invariant set of A are inside this one due to the fact that the union of invariant set is an invariant set. This invariant set is called an attractor because here it is stable. Moreover, it is more than an attractor. It is well known because it is a strange attractor. So why it is a strange attractor? Because it has a fractal structure.